Hello everyone, welcome back to Machine Organization and Programming. Today we're going to be taking a look at different number systems, in particular binary and hexadecimal. We'll then be looking at how our C code can access some of the information and give us clues about how those numbers are stored in memory. And then we'll take a look at the memory model, draw a picture of the memory, and think about where the numbers are, how they're laid out in memory. If you remember from last time, we were generating this very short program that just added two numbers together and stored the result in another variable. In this program, we were using integers. So we'll start by talking about how the computer is going to represent integer values. So first off, at the lowest level, we're going to be working with bits. A bit is just going to be a binary digit. It's either going to be a 0 or a 1. And this goes back to the way the computer hardware works. The circuits, the little wires that interconnect things, and the transistors that store the data on chips can either have a high voltage or a low voltage, or a high voltage or a zero voltage. And so it's those voltages that we use to get either the representation as a 0 or a 1. So that's where that comes from. And to come up with something that's got more than two choices, we just use more bits. So in computer science terminology, a byte is going to be 8 bits. Here I've got an example right here, 000111011. Okay? These bits are numbered from B0 over here on the right, B1, B2, all the way up to B7 on the far left. The most significant bit, that would be the one that contributes the biggest amount to the number, is the B7 bit, and the least significant bit is B0 over on the right side. So this is like the ones place, and the twos place, and the fours place. So how many numbers can we represent using only 2 bits? If we write out all the different combinations, 00, 01, 10, and 11, we see there's only 4 possibilities. 0, 1, 2, and 3 in this case. And the math formula that we use to do this mapping looks something like this. We're going to take the value in the most significant bit. So in this case, let me do this example right here. We've got a 1 in the B1 position, and we're going to multiply that by 2 raised to the first power, which is 2. And then we'll take the least significant bit, B0, and that's going to get multiplied by 2 raised to the 0 power. As we get to larger and larger sizes, we'll see that the 1 here and the 1 here, 0 here, 0 here, those are always paired up together. So in this case, we'll have 1 times 2 and 1 times 1, and that gives us 2 plus 1, so 3. So the decimal version of this, I'm sure everyone here is familiar with this. If I have a number like 39, I have a decimal digit 0, the tens place, D1. So I'll just take the D1, which is 3 here, multiply that by 10, and the 9 here in the ones position, that gets multiplied by 10 to the 0, or 1, and I get the number 39. So it works exactly the same as our decimal system, except that the place system is 1, 2, 4, 8, 16, and not the ones, tens, hundreds positions. So let's take a look at a little bit bigger numbers now. How many numbers can we represent using 3 bits? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. I can write them all out, but as we get to more and more bits, that's going to become troublesome. I don't have enough screen space for that. So a little bit different way to think about that is that I can have any one of 2 bits right here. 2 choices. I can have a 0 or a 1. I can have a 0 or a 1 here, so that's another 2 options, and a 0 or 1 here, so that's another 2 options. So that's choosing 2, choosing 2, choosing 2, and I can just multiply those together. 2 times 2 times 2, or 2 to the 3rd power, and that gives me the 8. So how many numbers can I represent using 4 bits? Again, 2 times 2 times 2 times 2, or 2 to the 4th gives me 16 different possibilities. Okay, now when we represent an integer on a 32-bit computer, like we were doing in the program sum.c, I've got int a right here. Let's take a look at that one. Integers are typically 4 bytes in C. This depends on the compiler, and we actually have a number of different types of integers we can use. There's short integers and long integers, and they have different numbers of bits that are reserved for them. But typically, the normal int, like this one that I'm using right here in the code, is 4 bytes. So that means that with 4 bytes, there's 8 bits per byte. I've got 4 of them. I've got 32 bits total. So here's an example. This could be a number that I'm storing in memory. 101101001001 dot dot. You guys get the idea. It's a lot of stuff to say. So yeah, that's a lot of zeros and ones. So what we're going to do is shorten this up a little bit by introducing a hexadecimal representation for these numbers. So the idea with hexadecimal is that I'm going to be using 16 digits to represent the number. I'm going to take the 0 through 9, and they'll have the same numerical value. But then I'm going to have a 10s, 11s, 12s, 13, 14, 15, and I'll use A for 10, B for 11, C for 12, 13, 14, 15 for the rest of these. So that gives me a different number system that lets me still write binary digits. So remember that if I had 4 bits, that way I could represent 16 different numbers. A couple slides back, I had the 2 times 2 times 2 times 2. What this is going to do is that's going to tell me that for each set of 4 bits in a binary number, I can use that to map to one hexadecimal digit and take that 32-bit number that was a mouthful to read off and shorten it up significantly. So here it is. Here's that number. So let's go through and just take a look at this. So I'm going to look at this very first set, the 1011. All right, so this is the ones place. So it'll have a 1 plus the 2's place plus 2 is 3. This is the 4's place. That's a 0, so I don't include that. And the 8's place. So 8 plus 3 is 11. And 11 in hexadecimal is going to be B. Okay, this next one over, 0, 1, 0, 0. This set of 4 digits right there. The 1's place, the 2's place, the 4's place gives me a 4, and nothing in the 8's. So this will be a 4. So if I've got B, 4. All right, check this out. 1011 is the same thing I just did. 1011. So that'll be B again. Then 1001. This is the 8th place. Plus 1 is 9. One more is 9. So that'll be 9. 1010 is the 8th place. Plus 2 is 10. So that'll be an A. 1011. That's the first one I did. That's B. 1011 is the one I just did right there. Let me think that was 8 plus 2 is 10. So that'll be A. And 1111 is 8 plus 4 plus 2 plus 1 is 15, or F. Well, let me see if I got that right. B4, B9. Yep, it looks good to me. I think I did it right. Okay, so when we write hexadecimal numbers, we actually prefix all of them with a 0x. This is the number 0, not an O. And this is just a clue that we're giving the computer or the compiler that I'm about to write a number in hexadecimal. There's another number system out there too, octal, which prefixes all of their numbers with the 0. So like 09 would sell it that, or 06, like it's June right now, 06 would represent an octal number 6. 09, octal only uses the digits 0, 1, 2, 3, 4, 5, 6, 7. So as soon as we get to September and you start writing 09 for the date, it thinks it's a hexadecimal number and crashes because it's an error when it doesn't recognize that the 9 is a digit. So just heads up there, I make that mistake all the time with computers and dates. Yeah, all right. So anyway, the prefix 0x is just a clue for the humans and compiler that the stuff that follows is a hexadecimal digit. Okay, all right, demo time, Mike. Go do this. Okay, so you guys at home, pause the video. Go ahead and log into your CS account. Get onto a lab machine and try this out with me. Okay, I just pulled up Putty. For you guys at home, I thought maybe one more time if you want to see this might be good. So I'm using a Windows machine, as you can see from the background there. The little Windows icon is in the corner. So I'm using Putty to connect to the lab machines. If you're on a Mac or a Linux machine, you can just open up your terminal. If you need help doing that, stop by office hours, and you can just type SSH and then the name of the computer you wish to connect to directly into the terminal. Can't do that on Windows, so I'm using Putty. 1 second. Doescher at best-linux.cs whisk edu. There we go. Okay, we're in. Oh, it's tiny again. All right, timeout. Okay, I'm back. I got it made bigger. Okay, password. Try that again. Okay, good. We're in. Let me see, where am I? I'm in my home directory, and I'm going to switch over to my teaching directory. So yep, I'm there. And let me think. I had, yep, directory for this class. And then we'll need a folder for lecture 2. Okay, now what I'd like to do is just write a program that's going to convert some numbers between hexadecimal and decimal and just print them out. So let's call this hex.c. All right, excellent. So I'm going to need, well, my main function, int main. So it's a function, so it needs to return something. And in this case, main returns an integer. So we'll put return 0 at the end. There, that's the absolute minimum I need for a functioning program. Also, what I would like to do is create a variable that just holds a number. Int num is equal to, in this case, let's put in that number. What was it? OX B4B9ABAF, I think. There we go. So now I have that number stashed, and that needs to be 0. Let me just double check to make sure I didn't screw that up. 0. Okay. And if I want to print this out, let's go ahead and do that. So we'll call printf, and then num equals, and then I need to put in the number, so that's going to be my percent. I've got some choices here how I want to represent it. I could represent it as a hexadecimal number with this. There we go. And now the number that gets inserted into my format specifier there is num. So that should print this out as a hexadecimal digit. Whoops, typo. What did I do wrong? Failing. All right, let me type that again. Hold on. I don't know what I did. Lost the whole line there. Printf. Num equals percent x, comma num. There we go. I can also print it out as a decimal number, percent %d, and let's just start with those two, see what this looks like. Oh, I'm also going to get an error if I do not include, so I need my compiler directive here, include stdio.h, because that's where printf is located. All right, this should be good now. So I'm going to write, quit, and then compile this. So I want to compile GCC is my compiler. The output file, I want it to call hex. My input is hex.h for a 32-bit machine, and all the warnings. It's not hex.h, it's hex.c. There we go. Okay. All right. And now if I run this, oh, let's put some end lines in there. Hold on. There we go. It looks so much better. Okay. So the first thing is the number being printed out in hexadecimal. This is the exact number that I just put in. It's made two changes here. It's done it in lowercase, and it has not put in the prefix, the 0x, to indicate that it's hexadecimal. It doesn't. The printf function doesn't do that when we take it out. And second, when we printed this out as a decimal representation of this number, inside the computer, it's all just ones and zeros. It's a string of 32 bits. And it can, the printf function is choosing to decide how to display this. And so it's just now representing this number as a decimal number, negative, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 1,262,900,305. All right, guys, it took a second to decide what I want to do next. And the next thing I'm going to do is jump into the memory model, a description of how the computer thinks about memory and where it writes down all the numbers. And to introduce this, I want to go back. I've got this variable num right here. I just printed out the contents of that number in hexadecimal and in binary, or in decimal format. What I want to do now is actually show you guys the address where this number is stored in memory. So I'm going to go back up, type on the right screen. We'll take this, and one of the things that C lets me do is actually get really close to the memory. I can print out the address of num is equal to, in this case, the address is going to be %p. Throw a new line on there, and the operator ampersand stands for address of. So this is address of num. And now if we go ahead, right, save that, and then compile it, and we'll run this again, I can see the address is actually presented in hexadecimal. And this is just, what do we got? 1, 2, 3, 4, 5, 6, 7, and 8 hex digits. So in each hex digit represents 4 bits. So this is a 32-bit number. And that's where, this is the location where that number is stored in memory. The first byte of this number, the most significant byte, is stored at that memory address. Okay, I'm going to pause here. I'm going to jump back over to PowerPoint, and I'm going to pull up a picture of this memory model. All right, here we go. I put together a picture of some memory. What I have here are just a bunch of slots where I can write down a number. And this particular memory model has 16 different slots. They're numbered 0 through 15. And each one of these holds 1 byte, or 8 bits. So if I have 16 memory addresses, that means to write out the particular addresses, I only need 4 bits to get to a total of 16 different numbers. So I can use 4-bit addresses for these. The computers that we're compiling for are 32-bit machines. Modern machines are 64-bit machines. All right, so let me jump to the next slide here. Now, suppose I wanted to store a 4-byte integer. In this case, I'm just going to go with hexadecimal representation B. So when I put all of the hexadecimal digits in, 0, 0, 0, 0, 0, 0, 0, B, that should have been 7 zeros and a B. And I want to store it at address 4. What does this look like in the memory? If it takes 4 bytes and each one of these are 1 byte, this is actually going to take up 4 different slots in memory. And so as I go through here, the first hexadecimal digit is a 0. So that's going to be 0, 0, 0, 0 in binary. The second one is a 0. 0, 0, 0, 0. All right. 3, 4, 5, 6, and 7 are all zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And it's not, when we get to B that we see something that's non-zero. So B is the hexadecimal representation of 11. And an 11 has an 8 plus a 2 plus a 1. So we should be looking at 1, 0, 1, 1. We're just missing the 4. All right. So that's kind of what this is going to look like, is we'll see that it takes up 4 spaces. This is really important because when we put the next one in memory, we find they won't be sequential. They're going to skip places. So the first integer is going to be stored at 4. The next integer will be stored at 8. The integer after that will be stored at 12 because they each take up more than 1 slot. And it's just going to return the starting address. So even though all the good stuff that's going on is actually not happening until we get to memory address number 7, these are all just filled with zeros. We're going to find this is really very common for when we're working with smaller numbers. Okay, so now let's take a look at like a real machine and what we've got available to us. The question I want to look at is how much memory is available to a program running on a 32-bit machine? How many addresses can it actually take advantage of? So the answer is going to be 2 raised to the 32 power. And somewhere around here, I do have a calculator. I don't see it. All right, so we're going to do this the hard way. I'm going to take this and break it into 2 parts. I'm going to split this into 2 to the 2nd and 2 to the 30th. And then I'm going to remember that we'll come back, 2 to the 2nd power is just 4. 2 to the 30th, though, we can say that 2 to the 10th power is 1024. That's 1 kilobyte. It's approximately 1,000. 2 to the 20th is going to be approximately 1,000,000, 1,000 times 1,000. And that's 1 megabyte. And 2 to the 30th is about 1,000 times about 1,000 times about 1,000, or 10 to the 9th, or 1 gigabyte, roughly 1 billion. And I'm saying roughly because I ignored the 24 here when I got to a million. I just said 1,000 times 1,000 is a million, and it's a little more than that. All right, so I'm coming back to this. I've got 2 raised to the second power is 4, and 2 to the 30th is 1 gigabyte. So that's approximately 4 gigabytes of memory is all that's available on a 32-bit machine. All right, I'm going to leave this as an exercise for you guys, or maybe for like an exam or a quiz or something. How many addresses are available on a 64-bit machine? It's a big number.